Hi everyone, I hope you're okay, and I hope that the videos will keep uploading and helping out. This is the 8th video, guys, where I'm tackling questions on chemical equilibrium. Please, guys, do expect a total number of 8 videos since the worksheet had 8 questions in total. So please, guys, do take this seriously, guys, because all of these questions are extracted from past exam question papers, and I strongly believe that knowing how to tackle exam questions will give you an edge whenever you write your final examination. So please do share the video to your peers so that they may have an edge as well. And please, guys, do help us grow the channel by just subscribing. Okay, we are being told that 1 mole of pure hydrogen iodide gas is sealed in a 1 cubic decimeter container at 721 kelvins. Equilibrium is reached according to the following balanced equation. Okay, uh, it is found that 0.11 moles of iodine are present at equilibrium. Firstly, they want us to state Le Chatelier's principle. It simply states that whenever equilibrium in a closed system is disturbed, the system will reinstate equilibrium by just favoring the reaction that will counteract or oppose the disturbance. Are you together? Whenever equilibrium in a closed system is disturbed, the system will reinstate equilibrium by just favoring the reaction that will oppose the disturbance. Or you can simply say that whenever equilibrium is disturbed in a closed system, the system will just shift to the side that will oppose the disturbance so that equilibrium may be reinstated. Okay, 6.2.1. Okay, they want us to determine the number of moles of each of the following at equilibrium. Firstly, they want us to find the number of moles at equilibrium for hydrogen. Okay, remember that, guys, initially we only had hydrogen iodide together, but as the reaction progressed, we ended up forming hydrogen gas as well as iodine. Are you together, guys? So since both iodine and hydrogen have the same stoichiometric coefficient, the ratio is just 1:1. So the number of moles of iodine that are formed will simply be equal to the number of moles of hydrogen, since the ratio is just 1:1. At equilibrium, we will just have the same amount. Are you together, guys? Okay. Now I want to know how many moles I have of hydrogen iodide at equilibrium. Firstly, I can simplify the number of moles of my hydrogen iodide that were used. How can I do so? I know that 2 moles of hydrogen iodide will simply give me 1 mole of iodine. But now, guys, I did not form 1 mole of iodine, but I formed 0.11 moles of iodine. I want to know how many moles of hydrogen iodide will I form. So therefore, X, which represents the number of moles of hydrogen iodide that I will use to form my iodine, is basically 2 times the 0.11. That's just 0.22 moles. Are you together? These are the number of moles of my hydrogen iodide that I will use. However, at equilibrium, I'll simply have 1 mole initial moles minus the number of moles that I used, 0.22. And then that will simply give me 0.78. Let me confirm. 1 minus 0.22. Yeah, it is 0.78 moles. That's how, guys, you're supposed to tackle that question. Okay, and then now we are told that the equilibrium constant Kc at 721 kelvins is just 0.02. Okay, and then the temperature of the container is now increased to 850 kelvins. The new equilibrium constant Kc is 0.09. Okay, so with an increase in temperature, the equilibrium constant also increased. I can therefore conclude that the forward reaction is endothermic, because Kc, an increase in temperature will increase the equilibrium constant if and only if the forward reaction is endothermic. Ne? Okay, let's use Le Chatelier's principle to answer that. Kc, guys, can only be increased if ever the products are increased as well. Are you together? If the products are increased, the Kc will increase. Why do I say so? Remember that, guys, equilibrium constant is just equal to the concentration of products divided by the concentration of reactants. If I increase my products, that means I'll be increasing my Kc as well. Okay, so equilibrium constant will only increase if and only if I increase the products. Are you together, guys? And for me to increase the product, that means I need to favor the forward reaction. Are you together, guys? So if the forward reaction is favored, it simply means my forward reaction is the one which is endothermic, because an increase in temperature will always favor an endothermic reaction. So if, guys, whenever I increase my temperature, the Kc increases, that simply means the forward reaction is endothermic. Please, guys, keep that in mind. Yeah? The forward reaction is endothermic. Okay, now they want us to calculate the mass of hydrogen iodide present at the new equilibrium. Okay, I have my hydrogen iodide. I also have my hydrogen over there. I also have my iodine. Okay, let's write over there. Then that's our concentration. No? Okay. These are initial moles. The change in moles at the new equilibrium, then the concentration at the new equilibrium. Yeah? Initially, guys, we will take our initial position from the previous equilibrium. At equilibrium, we had 0.78 moles of hydrogen iodide, and we also have 0.11 moles of hydrogen, and the same amount for iodine. Are you together, guys? Okay, they want us to know the mass of hydrogen iodide present. Okay, they never gave us the quantity of any of the three at equilibrium. So all you have to do, guys, is to just find the change, or rather the used or produced number of moles. Né? Let's focus on that row over there. Let's say yes, at the new equilibrium, I had 0.11 of hydrogen. Are you together? But then as temperature increased, that let's say I have gained X amount of moles for hydrogen. So since the ratio is just 1:1, that means I'll also have X over there. However, for my hydrogen iodide, the ratio is just 2:1. So I'll simply have 2X over there. But remember that, guys, an increase in temperature favored the forward reaction. That means my reactants decreased and my products increased. So over here, I'll simply have 0.78 minus 2x, and then over here is just 0.11 plus x. Same thing applies, plus x. Now, the volume, we were given the volume as, where's the volume? The volume, oh, there's the volume. It's 1 mole per cubic decimeter. So for us to find the concentration, we just need to divide the number of moles at equilibrium by 1. And hence the concentration at equilibrium will simply be 0.78 minus 2x, 0.11 plus x, another 0.11 plus x. So I can therefore go and calculate x and then go and find the mass of my hydrogen iodide at equilibrium. The equilibrium constant expression, it's simply the concentration of the products divided by the concentration of reactants. Né? My product is just hydrogen as well as iodine. it's hydrogen as well as iodine, ne? But for my reactants, I simply have hydrogen iodide. Please note that, guys, these concentrations are raised to the stoichiometric coefficients. Ne? Over there, the stoichiometric coefficient for hydrogen iodide is 2. That's why I have a squared over there. Ne? And then the stoichiometric coefficient for both hydrogen and iodine is 1. That's why I don't have the exponents over there. Okay, I was told that the Kc value is just 0.09. Let me confirm. Yes, it's 0.09. The concentration of hydrogen is 0.11 plus X. The concentration of iodine is also 0.11 plus X all over 0.78 minus 2X all squared. Ne? I still have 0.09. I'm multiplying two things that are the same, guys. Ne? My numerator, I'm multiplying two things that are the same. I can simply take both of those things. 0.11 plus X all squared is the same as saying A times A. This will just give me A squared. We are going back to our exponents. Ne? And then at the bottom, I simply have 0.78 minus 2X all squared. For me to solve X, guys, let me just remove those squares over there. Ne? Just take the square root on both sides. Then we'll end up having 0. What's the square root of 0.9? 0.09. Square root of 0.09. That's just 0.3. And then I'll simply have 0.11 plus X all over 0.78 minus 2X. Now, I can just cross multiply over here. I'll end up having 0.3 multiplied by 0.78 minus 2X is just equal to 0.11 plus X. And then 0.3 multiplied by 0.78 will just give me 0.234 minus 0.3 times 2. This is just negative 0.6. That's equal to 0.11 plus X. 0.6X rather. Ne? I can take the 0.6X to the other side. It will be positive. On the left hand side, I'll simply have 0.234 minus 0.11 is equal to X plus 0.6X. 0.234 minus 0.11, that will just give me 0.124 is equal to 1.6X. Divide both sides by 1.6. And then X is basically equal to 0. Let me check. 0.124 divided by 0.124 divided by 1.6. Yeah, that's just 0.0775. So X is just 0.0775. Now, guys, so I now, for me to find the mass of my hydrogen iodide at equilibrium, I know that number of moles is equal to mass divided by the relative atomic mass number. Are you together? And hence the mass is just equal to number of moles divided by molar mass. Okay, how can I find number of moles? Number of moles, I simply have 0.78 minus 2 multiplied by 0.0775 as my X, and then I need to multiply this by my relative atomic mass number. Hydrogen, the relative atomic mass number is 1, and then iodine, I simply have 127. So this will just give me 0.78 minus 2 times 0.0755. No, 7 1.75 rather, multiplied by 1 plus 127, I'll simply get 80 grams. So the mass at equilibrium, guys, for my hydrogen iodide is just 80 grams at the new equilibrium. The mass of hydrogen iodide in the new equilibrium is just 80 grams. That's how, guys, we're supposed to tackle this question over there. So please, guys, do stay tuned and wait for more videos. Thank you for your time.